Assalamu alaikum. This is a snake ladder game project that we, Team Beta Per Second, developed for our EEE 4308 class project. This is a digital hardware-based implementation of our classical snake ladder game. The system comprises interconnected modules that manage gameplay logic, player interactions, and real-time visual feedback on a 4x4 LED grid. Here's a breakdown of its architecture. The core modules include the dice module, which generates random number ranging from 1 to 3 using a high-speed counter 555 timer IC and displays the result on a 7-segment display. The ladder and snake lengths and heads are manually predetermined. The player selector module within the dice module toggles between player 1 and 2 with the switch, ensuring alternating turn. The active player is indicated via LEDs. Snake and ladder logic module computes the next player position by adding the dice value to the current position. It checks for collisions with predefined snakes, which reduce position, or ladders, which advances positions using comparators and adders. The memory module stores and updates player positions using 4-bit D-type flip-flop registers. It interfaces with the logic module to update positions only during active turns. The mode module, a 4x4 LED grid where each block has 4 LEDs. Player LEDs being red and blue showing real-time player positions, and snake or ladder LEDs being green or yellow marks fixed obstacles respectively. Winning module compares player positions to 15 binary 1111. In a match, it triggers LEDs to signal victory. The reset module resets all player positions to 0 via a debounced push button. Decoder modules include position decoders converting 4-bit player positions to activate specific LEDs on the grid, whereas snake or ladder decoders calculate head or tails for snakes or top or bottom for ladders positions using adders or subtractors and lights corresponding LEDs in the grid.
Now more about the individual modules and interactions between them. The visual interface of the board game is the 16 blocks of LEDs, each block holding 4 LEDs, red, blue, green, and yellow. The former two show the position of the players, whereas the latter two show ladder and snake respectively. At a time, only 6 LEDs are lit up in the grid. Before starting the game, we manually select the snake and ladder startings and endings, which are displayed in the LED grid once we start the simulation. A snake position decoder and a ladder position decoder from this input calculate the starting and ending of the snake and ladder and light up 4 LEDs, 2 for snake starting and ending and 2 for ladder starting and ending. The player LEDs light up in the first LED block. The game starts once we press the dice module switch. It generates a random number from 1 to 3, and the generated binary number is sent to the snake ladder logic module along with a clock signal, CLK signal, generated from the JK flip-flop in the toggle mode to toggle between the players in the memory module. The clock signal also lights up the current player indicator LED. A debouncer circuit was used with the push button to prevent multiple unintended signals caused by signal bouncing. An RC circuit consisting of 2 resistors, a capacitor, and an inverter was chosen for this purpose. When the button is released, the capacitor charges through the resistors, reaching a threshold that makes the inverter output 0. When pressed, the capacitor discharges, dropping below the threshold, and the inverter outputs 1. This process smooths out voltage changes, eliminating bounce and ensuring clean signals. The output of the debounce circuit is connected to a 555 timer configured as an astable multivibrator, which continuously oscillates between high and low states. The oscillating signal serves as the clock pulse for flip-flops in a counter circuit, generating a random number between 1 and 3, simulating a dice roll. The challenge is to control the oscillation frequency so that the number appears random, unpredictable, yet is slow enough to be observable. The frequency is determined by components R1, RV1, and C1 in the circuit. The following is the equation of the frequency. We have made RV1 to be variable resistor, so we could control the frequency as needed.
We can control the frequency here by changing the RV1. Once we have the resistor as 1 kilo ohm, when we push the button, we see the clock running. Now when we change the frequency to 50 kilo ohm, and push the button, the clock moves much faster here. Thus, we can choose our desired frequency from the variable resistance.
For 2-bit synchronous up counter, we need to count 1 to 3, 0, 1, 1, 0, 1, 1 in binary, in our desired frequency for the dice. For 2 bits in the binary system, we need 2 flip-flops to design the up counter. We have chosen JK flip-flops here. The output of the 555 timer goes as the clock signal of both of the JK flip-flops. For determining the flip-flop inputs J0, J1, K0, K1, we drew the state table, and with the help of Kmap we obtained the required equations, the process of which was included within our report. And the output of this module is shown in the 7-segment display. The snake ladder logic module takes the dice, snake head and ladder head and length as its input. With the snake ladder logic module, the current position of the current player is added using an adder. This new position is first checked with the 111 checker to see if the player count has exceeded binary 1111. If so, the dice number is subtracted and the player remains in its current position. Otherwise, a comparator is used to check if the player should ride a ladder, and is done so accordingly, and moves to the comparator and adder for its encounter with snakehead. Following the same process, the result is the current position of the current player. This current position is sent to the memory module, where it stores the current player's position. The memory module in the snake ladder game is designed to store the positions of 2 players. It ensures that only one player's position is updated at a time while maintaining the integrity of the game logic. The circuit consists of 2 memory units for the 2 players, a demultiplexer, DMUX, and a clocking mechanism. There are 2 parallel in and parallel out memory units used to store player positions. The RC branch is added to calibrate the memory with the game. DMUX routes the stored player position to the snake ladder logic module based on selection input. The reset input allows resetting player positions to 0, 0, 0, 0 when required. The circuit operates by updating the player's positions based on the output of the snake ladder logic module. When the dice is released after the click, the current position of the selected player is sent to the snake ladder logic module L3 to L0. This current player position is updated after taking the dice input when push button is released in the snake ladder logic module, and this value again is sent to the memory unit I3 to I0. The clocking mechanism of the memory module uses the player selector signal from the dice module instead of the usual high frequency memory clock. The NOT gate ensures that the memory unit of the active player is activated and the other is deactivated. After the dice button is released, the flip-flops in the active memory are triggered and the position of the current player gets updated. The CP of the DMUX is basically the selection pin that gets low signal when player 1 is selected and sends the player 1 position to the output side, and gets high signal when player 2 is selected and sends player 2 position to the output signal. Then this output signal goes to the snake ladder logic module again. The player positions go to the player position decoders and winning module. All these steps are automated as the player position in this game automatically changes with each push button press. The memory outputs both the player position as an input to the 2-player position decoder, which then lights up the LEDs in the grid to indicate the current position of each player. This output is also sent to the input of winner module, which is designed in a way with AND gates that if a player is all 1 or 1 1 1 1, it lights up the corresponding LED to indicate it has won. Otherwise, the process keeps on going with alternating players until a player has won. The reset module restores the game to its initial state by resetting both players' positions to the starting point 0 0 0 0 without requiring a system power cycle. Upon activation, it sends a high signal RST to the memory module, triggering the reset. To ensure reliability, a debalanced circuit comprising a 10 kilo-ohm pull-up resistor R2, a 1 kilo-ohm discharge resistor R3, a 1 microfarad capacitor C5, and a hex inverter for signal inversion and buffering eliminates mechanical switch bounce, stabilizing the signal before execution. An LED provides visual confirmation that the game is ready to restart. This design guarantees a clean, accurate reset action.
This is the flow of the interaction between different modules explained before. Here some colored arrows represents being part of the same process.
Assalamu alaikum everyone. Now we'll be testing each of our individual modules as how they work through the process. Starting with the dice module. In the integration part, the explanation of this module was given, so I'll be skipping that part. What I'll be demonstrating now is if it works as mentioned. So if we look at the dice module here, there's an input of the push button, and the output of it, which is dice click here, goes into the player selector module, indicating which player is selected as of now. Going to the child sheet. So as you can see that there's a JK flip-flop which is in toggle mode. Here's the JK flip-flop, and its output goes as the dice click into the player indicator circuit. So whenever we'll be getting a 1s clock pulse here, this output will be toggling from 1 to 0 and 0 to 1. Coming back here, the other two inputs go into the snake ladder module, so that will be discussed later. As of now, if we look into the settings, there's a logic probe set with the push button. Whenever the button is pushed, the flip-flop toggles the output from 1 to 0 and vice versa. Let's check it. This output goes into the player selector module. If we see the modules together, then as we can see, whenever the button is pushed, then the toggling output toggles between 0 and 1, which indicates the player that is selected. In this case, whenever there's logic 1 in the dice click, then the selected player is player 1, which is indicated by the red LED, and whenever the dice click gives out logic 0, then the blue LED lights up, indicating that player 2 is currently selected. Coming to the ladder position decoder, if we look at here, these are the parameters that are to be set manually. This is the ladder head and this is the ladder length. Let's set these as 0101 and 0111. So if we look into the child sheet here, we have connected logic probes with the inputs and outputs. So as we set the inputs such that the ladder length is 0111 and ladder head is at 0101, which is in decimal 7 and 5. So in the output, what we'll be seeing is that as the board module's spot starts from 0, the 6th logic probe for the 5th block in the board module and the 13th logic probe for the 12th block in the board module will be giving us a logic of 1. These being connected to the LEDs going to the parent sheet, what we can see is that the 5th and 12th green LEDs are lit up, indicating the start and end of the ladder. Moving to the snake position decoder, these are the manual parameters here as snake head and snake length. So setting the parameters here as snake head is to be at, let's say, 1011, which in decimal is 11, and snake length is to be 0101, which is binary for 5. So similarly, we've connected logic probes to the input and outputs here too. Analyzing the logic probes, in the output, we can see that we are getting logic 1 at the 12th and 7th probe, which are respectively indicating to the 11th and 6th block on the board modules as it starts from 0. So these connections are eventually connected with the yellow LEDs on the board module. Going to the parent sheet, we can see that the corresponding LEDs are lit up for the respective inputs of the snakehead and snaketail. So this is the snake ladder logic module and memory module. As their functions are interconnected with each other, we'll be presenting them together. Now, to show the inputs and outputs of the modules, we've connected logic probes here. And to ensure that the players are facing a ladder, we have set some parameters manually. We set the dice head at 01, which is the binary for 1. The ladder is set to start from the third mark block for experimental reasons, which is represented by the 0011, and the length might be whatever we want it to. Here is the clock pulse. As we are not using the push button of the dice module here, we'll be giving the clock pulse manually here. Each click of the mouse will be counted as a dice click, hence clock pulse in this case. These represent the current position of the corresponding players, this of the player 1 and this of the player 2. This is the input from the memory module of the current player's position. And this here is the position of the selected player after adding the dice value. So as we start the simulation, after each click, we can see at first the player 1's position changes by 1, which is the dice value. If we continue to do this, the second player's position changes by 1. So if we keep doing this until one player reaches the ladder head mark, which is at 3, we will see that one player reaches the ladder head, we will see that it will ascend to the 1010 mark, the 10th marked block, as we've set the ladder length at 0111, which is 7. So this is the winner module. This is only activated when one of the players reaches the 15th mark, which in binary is 1111. When a certain player reaches that 15th mark, that player's corresponding LED lights up in the winner indicator module, showing the indicated player has won. Let's change it up to the player 2, and we have our corresponding LED lit up here. If we go to the child sheet, we have connected logic probes in the output and in the inputs and the outputs. So from here we can see that too. So this is the winner module. Here is the reset module. As we can see, this is the player's current position at 1. If we push the button here, we can see a 0 at the reset node and a 1 at the output RST node. This RST signal goes into the memory module to the reset of the D flip-flops. Whenever the button here is pushed, all the player's positions are resetted, hence turn back to 0.
Now let's play the game.
Setting the parameters here, we can actually set the parameters of the ladder head, ladder length, snake head, and snake length by ourselves. From the right, we have the LSBs, and to the left, we have the MSBs. So we can set these things manually. So let's set this. So as we can see that the corresponding LEDs, according to the input we've given here manually, the LEDs are lit over here. The snake head at the 13th mark and its length is 4. So at the 9th mark we have the snake LED lit up, and also for the ladder it's the same. So starting the game, we click on the push button of the dice module and then roll the dice. So the dice showed 1 and player 1 moved 1 step ahead. Yeah. So as we are playing, we can see that the player selector module is now set at the blue LED, indicating the player 2 is now selected. So whatever the value of the dice will be showing here, this player will be moving that much steps ahead. So if we proceed as it is, so what happened was the blue, that means the player 2 was at the 11th mark and the dice rolled to 2, and the player 2 went up to the 13th mark, but there we have the snake head. Yes, the snake head is at the 13th mark. So the player blue went to the snake's head, and the snake's length was 4, which means the snake's tail was at the 9th mark. So the blue player from here, the 11th mark, went up 2 steps ahead, and at the 13th mark, at the snake's head, it came to the snake's tail at the 9th mark. So the player 1 has reached the 15th mark, and as you can see that at the winner module, The red LED is lit up, indicating that the player 1 has won the game. Now if we push the reset button here, then everything will be reset again and the player's LEDs will be continuing from the 0 spot here.
Thank you everyone. That was all from our side, and we're team